Okay, we're going to start the screencast on gases. And you should know something about gases because you should have had conversations about the states of matter, at least in middle school. Solids, liquids, and gases. But we're going to focus on gases. Okay, kinetic theory of gases. You've heard of kinetic energy. It's the energy associated with movement or motion. Okay, in gases, they consist of small particles. And there are several points that you need to keep in mind when we're talking about gases. That the particles are going to move quickly or rapidly in straight lines. They essentially have no attractive or repulsive forces to each other. Okay, so they bounce off each other perfectly with no loss of energy overall. They can transfer energy to each other. They are very far apart when you compare the distance between gas particles to the distance between particles in a solid or a liquid. They have very small volumes compared to the volume of the container that they occupy, so most of it is the space between particles. And then those particles have a kinetic energy that increases with an increase in temperature. And there's an important thing to note about that kinetic energy. Okay, that kinetic energy, if you remember, has a formula 1/2 mv squared, where m is the mass of the object and v is the velocity. It's important to note that for gases, the kinetic energy of any sample of gas is directly proportional to the temperature. Okay, meaning, at the same temperature, the same sample of gas, I should say any sample of gas with the same volume and mass, is going to have the same kinetic energy. Okay, that'll come up later. Okay, so states of matter. Fundamental difference between those states of matter, as I've said before, is the distance between the particles. Okay, you have the gas very far apart, moving randomly, bouncing off of each other very far apart. If we cool that down, what happens is the attractive forces between those particles start taking over. And it doesn't let those particles move free, totally free of each other. They're kind of held together, but they're free to move relative to each other. They can roll over each other, but they still are sticking somewhat close together because the kinetic energy is not enough to totally overcome those intermolecular forces. Okay, and then we go into the solid, a crystalline structure, or solid. Okay, that's a more ordered arrangement. Particles are in fixed positions. They still move, but the intermolecular forces between those particles are so strong, they're held in place. So they just kind of move slightly, but are not free to move at all beyond their vibrational motion. I hope I explained that well. Okay. Solids and gases, solids and liquids, because the particles are so close together comparatively to gases, they are referred to as the condensed phases. Okay, and those are just some terms that you should know. All right, again, the state that a substance is in at any particular temperature and pressure depends on two antagonistic or fighting entities, things that are at odds with each other. The kinetic energy of the particles and the attractive forces between the particles. So if the kinetic energy is enough, the temperature is high enough to overcome those attractive forces, the substance will be in a gas phase. If the intermolecular forces are much, much stronger than the kinetic energy, that's going to be the predominant force and the substance is going to be in a solid form. Somewhere in between, the substance is going to be in a liquid form. And those temperatures and pressures at which that happens depends on the substance and the intermolecular forces. Okay, so phase changes. Hopefully you're familiar with these from 8th grade. Okay, what I like to show is the difference. This is the energy of the system increasing. Okay, so really the lowest energy system is that solid because the temperature is low, the kinetic energy of the system is low. If I put some energy into the system, I'm going to go from the solid phase to the liquid phase, and that's called melting. If I add more energy, okay, I take that kinetic energy and those movement of the particles are enough that they start to overcome the intermolecular forces, and it through the process of vaporization or boiling, it becomes a gas. That's the highest energy state. I can sometimes, depending on the substance and the pressure, go from solid directly to gas, and that's called sublimation. And you usually see that around Halloween with the carbon dioxide forming fog. Okay, if we go the other way, gas going to a solid is called deposition, sometimes called reverse sublimation. Gas to a liquid, condensation. And liquid to solid is freezing. Okay, this should have all been pretty much a review. Something you haven't seen before, though, perhaps, is this kind of graph. Okay, and this is looking at the phase changes and what's going on kind of between the kinetic energy and what you could call the potential energy of the system. Okay, if you notice, okay, if I start off, and this is water, starting off at negative 25 degrees Celsius, if I increase the temperature and I add heat to the system, okay, I'm heating up that ice cube until I hit 0 degrees Celsius, and this is assuming atmospheric pressure or 1 atmosphere. Okay, so I'm affecting the kinetic energy. I'm making those particles move faster within their fixed positions until I hit the melting point of 0 degrees Celsius for water. Then if you notice, even though I'm adding heat, because that's what my x-axis is heat added to my system, notice the temperature doesn't change. But I am breaking apart those intermolecular forces, so I'm kind of overcoming some potential energy here. And that I have ice and liquid water. It's in the process of melting. Once all of the ice has gotten to the liquid phase, as I still add heat, the temperature and the kinetic energy of my system increases until I hit 100 degrees Celsius, the boiling point of water. If you notice, for a long time, as I'm adding heat into the system, I'm staying at 100 degrees Celsius. Again, that energy isn't going to increasing the kinetic energy of the system. It's going to break apart, it's going into breaking apart those intermolecular forces, that potential energy holding those molecules together. And it takes more energy, more heat added to break apart those intermolecular forces going from a liquid to a gas, because you have to totally overcome those intermolecular forces. This smaller amount of heat here was only partially breaking apart those intermolecular forces, just allowing them to roll over each other into the liquid phase. Okay. Here, a lot more energy has to go into it because I'm breaking apart or overcoming all of the intermolecular forces, totally breaking free these gas molecules. Once everything is turned into a gas, if I continue to add heat into the system, the temperature increases, the kinetic energy of the system increases. We'll look at this curve more when we talk about enthalpy or energy changes, but it was important to me that you understood kind of how adding energy is affecting both the kinetic energy and the potential energy, hence the phase changes of the system. Hopefully you can see too that I can go backwards. I could start with steam, take heat out of the system until I hit the condensation point. Okay, continue to remove heat from the system, change that gas into a liquid until it's all in a liquid form. Continue to remove heat, lowering the kinetic energy of the system until I hit the freezing point. If I continue to remove heat, I'm going to set those intermolecular forces up, changing it into ice, solid structure, until everything is ice or in the solid form. And if I continue to remove heat, I'm going to continue to lower the temperature and the kinetic energy of the system. All right, properties of gases. We really can define gas in terms of 4 properties. Its pressure, its volume, its temperature, and its amount, N. That N is the number of moles. Okay. One thing to note, this is hugely important. When we do calculations involving temperature and gases, it is extremely important that you remember that that temperature has to be expressed in Kelvin. Has to be in Kelvin, the absolute temperature. All right, let's talk a little bit more about pressure. Gas pressure is defined as the force acting on a specific area. So the pressure is the force over the area. There are several units that you should know. Atmospheric or atmospheres is one. Okay. 1 atmosphere is taken to be exact. There are millimeters of mercury. That's an important unit. 760 millimeters of mercury is the same as 1 atmosphere. They don't use torr a whole lot. We will look at inches when we do labs where we have to do atmospheric pressure, because that's typically how pressure is recorded in the environment in the US. Okay, but 29.9 inches of mercury is equal to 760 millimeters. You may be familiar with the term pounds per square inch, PSI. We won't use that one very often. And then there's pascals and kilopascals. All of these values are the same as 1 atmosphere. You may need to change units every now and then. All right, so how would we express 475 millimeters mercury in 1 atmosphere? Real quick, if you look at the factor label, 475 millimeters mercury times their 760 millimeters mercury in 1 atmosphere. That should be atmosphere, not atoms. Millimeters mercury cancel out. I'm left with atmospheres. I will let you do the math. Pause the screencast and do the math for the next one, and we'll look at the answers. So you should have gotten 0.625 for the first one and 1,520 millimeters mercury for the second. What do we mean by atmospheric pressure? Well, the definition is the pressure exerted by a column of air from the top of the atmosphere to the surface of the Earth. Okay? At sea level, it is taken to be 1 atmosphere. And we will use 1 atmosphere as the standard pressure. But it is that pressure exerted by a column of air, mainly oxygen and nitrogen, on the surface of the Earth. Okay, and the atmospheric pressure does depend on the weather, it depends on the altitude. It's lower at higher altitudes where the density of the air is less, and it's higher on a rainy day than